Okay, why don't we get started here? So let me give you guys some advice for the second time again. You guys just had lab for the last month. You guys, I don't mean to speak ill of any other teacher's styles, but his style is probably very much you're writing a lot of notes. Okay? I'm trying to change that. I want you guys to have the notes in front of you, but not so that you can ignore me or talk to your friend. I do it because I want you guys to be able to better engage in a lesson when we're talking. So here's some advice. Write down what I say. Highlight stuff, okay? But rather than having to be so busy handwriting stuff, what I'm really hoping for, guys, is your 100% attention. There are only 5 lessons I'm going to give in all of this physics. So rather than me talking every day for like 4 straight weeks, I'm only going to talk 5 times. This is one of those 5 times. You got to make sure you're giving me your best attention, okay? So put the paper airplanes away, put the spinners away. I see them, guys. Okay? Give me your best attention. So, here we go. Let's talk about physics. Physics is another one of the courses I teach, and I want to begin by talking about what physics is as a broad concept first. Why? I just said put it away. Okay, physics is the study of natural phenomena. Okay? What does that mean? Well, if I were to put that into like people words, it's about 2 words here. It's about energy and matter. Energy and matter. These are the 2 natural things that the universe has kind of given us. Okay? In our universe, we have stuff, matter. Does anybody remember from Unit 1 in chemistry what matter is? Can you just define it for me? Matter is anything that has, yeah, if it takes up space and has mass, it is matter. And chemistry is all about matter. Physics, then, is about matter and the other thing that we didn't talk about, which is energy. Because energy is not matter. Fire is a form of thermal energy. It's heat, but it's not matter. There's no mass to that. Does that make sense? So physics is now going to talk about how to bridge these things. The 2 natural things in the universe, the stuff we have, and the energy we use to move it around. Can I say that one more time? Physics is about the stuff we have, the matter that exists. You and me and this paper here and that door, that's our stuff. And then the energy that causes it to move around and do things. Because honestly, our world would be very boring if it just sat there and did nothing. This is boring. If we just all sat here the entire time and didn't move. This would not be an exciting universe. Does that make sense? But we have a wonderfully interesting universe where planets move around and things explode, right? Stuff happens. So, these are the 2 words we want to talk about. But today, we're really going to focus on this part of physics, the energy part. Okay? So hence the title of today's lesson. So a little bit of history here. This is really brief because this is not what you're being tested on, but I want you guys to know the basics here. The name physics, just so you guys know, came from the word nature. Okay? Because it's all about how the stuff around us works. Okay? We're trying to figure out the universe. Okay? There's a lot of similarities between chemistry, because chemistry is all about matter. There's a lot of stuff to do with astronomy in physics, like big picture universe stuff, like, well, why is the Earth spinning? And why is there a moon going around the Earth? And why is the Earth going around the sun? There's a lot of physics involved in that. And if you get to a certain point, there's a lot of math. You guys aren't going to do a lot of math, just so you know. But my high school physics students, huge amount of math skills. In general, we can divide physics up. Physics is actually divided on a timeline in a spectrum. If you guys were to imagine like the history of time, right here, let's make this today. Okay? Physics is actually divided up into 2 different sections. There's what's known as classical physics, and then there's now what's known as modern physics. And if you take physics from me in grade 11 and 12, we're going to talk a lot about this. Today I want to give you like the 2-minute version. Okay? But in about the year 1909, give or take, a guy named Niels Bohr came up with a model for an atom. And we talked about this in chemistry. Niels Bohr realized that electrons did not orbit. Does this sound familiar to some of you guys from our first unit? Discovered they didn't orbit. And he realized that electrons are actually found in energy levels, and they can literally teleport from one energy level to the next. And he opened up a whole new idea, which we now call the quantum realm. And it is some super cool and trippy stuff. Like lots of science fiction is based on this. Before that, before Bohr realized some of this stuff, most stuff fell into the idea of classical physics. And if you ever hear about these guys' names, Galileo and Newton, they're like more of like the historical people. But really, in about 100 years ago, things really shifted, and like Einstein came up with some of his crazy ideas about how like planets are actually not going due to gravity, but due to something called special relativity and stuff I don't even fully get. So, anyways, that's kind of like the brief idea of physics. I'm not going to test you on this, by the way. So please don't look at this slide and go, I got to memorize this. This is just, I put this on every single one of my classes that learns physics for the first time. I put this slide on there for them. Here's what I need you guys to know. We're going to talk about these two things, energy and matter, and how they go together. Now, in grade 9, we just focus on one kind of energy, actually, because there's so many different types. Okay. Before I get to all the different types of energy, though, I want to give a bit of a history lesson as to what scientists believed about energy over time. Again, think of this timeline right here as we go along here. Okay. I'm talking like thousands of years ago. Scientists had a theory about elements, and I think I actually showed you this in the chemistry unit. They believed that everything in the universe was made up of either earth, air, fire, and water. That's what they thought that stuff was made of. They were very, very wrong. What is stuff made of? Yeah, and where do we find the basic building blocks of matter in chemistry? On the periodic table. Yeah. There is no element of air. There is no element of fire. I mean, not only this, like, earth is, I guess, matter. But, like, fire is not matter. Fire is energy. Does that make sense? So, like, their first theories were, like, way off. They were so wrong. But that's what they believed that stuff was made of. Now, I want to fast forward a long time in the future. Like, that was 2,000 years ago. This is only 300 years ago. Scientists had a theory about energy. They thought that it was something called caloric. And we actually still use the base of this word today in the word calories. You guys have heard of calories before, right? Like, food has a certain amount of calories to it. The more calories you eat, the more energy there is. But then it usually leads to, like, obesity if you have too many calories. Okay. Well, we still use the root of that word today. But in the 1700s, they had a theory that stuff contained this thing called caloric. And basically the concept is that some stuff had lots of caloric and other stuff didn't have caloric. Okay? And so caloric would then go from warmer things to cooler things. Like if you were a cup of coffee had lots of caloric because it was hot. And it would give away its caloric somewhere else. That was their theory. Hot stuff had caloric. Cold stuff did not have caloric. Does that make sense? In hindsight, it's actually kind of a dumb theory. It doesn't really work that way. What they were really describing is this word right here. They were describing heat. They just didn't know how to put it in words yet. And so they thought that it was actually like a thing. They thought that there was like a matter, an actual substance that was leaving. But they didn't realize that what they were really describing was heat, and that heat is a form of energy, and energy is not matter. But they thought it was matter. They thought that this caloric was actually like a tangible thing that you could somehow like collect in the same way that I could like hold this matter in my hands. They thought that maybe you could like hold caloric in your hands. Does that make sense? So they're kind of right, but not really. There was a huge problem with this theory, though. And this guy named Count Rumsford, he came up with this hypothesis based on an experiment that he kind of saw or did. Okay, I want to take you back to like the 1700s again. One of the main sources of fighting would have been to use a cannon. You guys think like Pirates of the Caribbean, you know how they have cannons on the side of the ship? How do you make a cannon? A lot of metal, and you drill a really big hole in it. Basically, you have a large cylinder of metal, and you have to drill a massive hole through the middle of it. Does that make sense? Here's a picture of someone in a workshop right here, and they're making a cannon by like spinning a blade into the middle of it. And as they spin the blade into the middle of it, they're making a hole for the cannonball to go in. Does that make sense? Okay, so now that you got the context, here was Count Rumsford's problem here. When you had metal, metal is often very cold. Does that make sense? Which means, according to their theory, metal does not have caloric. The blade also does not have caloric because the blade is cold. But you guys probably know this. What happens when you start grinding pieces of metal next to each other? What's going to happen to this? It gets very hot. I mean, it's hot enough to burn. Okay? So this made no sense because this was cold when we began with. This was cold when we began it. But you start spinning the blade inside and it starts to heat up. And the question is, what is the source of the caloric? Where did this magic heat all of a sudden come from? Except they didn't know it was heat. You know what I mean? They thought it was an actual substance. And so this caused a huge problem because clearly there is no such thing as caloric then. What they didn't realize is that we were really using energy, yeah. And specifically to energy, it was causing friction. And we now know that friction causes something called heat, which we may use the word thermal energy. Anybody ever heard that before? Thermal energy? That's one source of energy. Heat is one of many sources of energy that we know of. And when you rub two surfaces next to each other, especially metal, it will heat up and it will create energy for us. Can anybody name some other forms of energy you know of? So there's heat. Electricity is actually the one we're going to focus on in this unit. Why are we able to see? Light's another form of energy. Why can you hear? Sound. Does that make sense? So there's actually many different forms of energy. And Count Rumsford is kind of the first guy that came to the conclusion that there's no such thing as a magical caloric. Really what was happening is because they were using energy to grind the two things next to each other, that energy was being converted into heat. And I have another picture here that I found online that kind of explains the idea of maybe how they ground the cannon. Because I don't think they did it by hand. I think this is really cool. They probably would have hooked up some sort of big pulley system here, where as the horses walk around in a circle, you guys can kind of figure this out, it's going to spin the main pole, right? And as this gear spins, it spins this gear, and then as this pole here spins right here, it's going to grind out the shavings and kind of make a cannon. Right? Now, this is going to get very hot. As this is made, the word we'd use is as we bore a hole in the cannon, it's going to heat up. But did the heat just magically show up out of nowhere? Well, no, because these horses, they had energy, right? They had the energy to be able to move. And as they moved this thing, it moved this, which moved this, which moved this, and then it converted it to heat. In grade 8, you guys should have talked about in one of your units, I believe it would have been about machines and systems. Has anybody ever heard of, what's it called again? One of those like machines that like you like knock over a domino and it knocks over other dominoes and then it causes something else to happen. You guys know what those are? I'm blanking on the name right now again. One of those like machines that's like really, yeah, right? Where like, what was that? Oh, there's a name to it. Do you guys know what I'm talking about though? Like where like a balloon pops and then it causes a bunch of dominoes to fall over. And then it's a chain reaction. There's a name for it. Oh my goodness, I can't believe I don't know it right now. Okay, anyways, do you guys feel like you know what I'm talking about here though? Okay, that's really the same thing that's happening here is energy was converting. One form of energy causes another one to happen, causes another one to happen, causes another one to happen. And energy can change forms. That's the big goal in our unit here, is I want to talk to you guys. I feel like you're losing attention here. I want to talk to you guys about all the different forms of energy and how they can change from one to another. So let me, oh, my board just turned off here. Uh-oh. This isn't good. Come on. Okay, there we go. Okay, can I skip this slide for a second? I'm going to come back because I think I can make a point more effectively if I skip ahead. Can you guys find this slide right here? And then I'm going to go back a bit. What Count Rumsford discovered is that there are many different types of energy, and they can be converted from one to the other. What I've got right here is a big list of a lot of forms of energy, from thermal energy, which is basically heat. Let's talk through some of these other forms of energy. What is chemical energy? Anybody know? Think of a battery. It's energy that comes from chemicals. As chemicals react with each other, they can produce energy. You guys remember when we did our chemistry labs and we lit things on fire? Well, where did that heat come from? It came from chemicals. So chemical energy turned into heat. Does that make sense? So like a battery would be a good example of this. We are going to focus in our physics unit specifically on this. This is where most of our attention is going to go. We're going to talk about electricity. Okay, that's a form of energy. Electricity can do so many things for us, though, right? For example, right now, electricity is giving us luminous energy. What's luminous energy in like people words? Light. Yeah. Electricity is causing these lights to turn on. Electricity is also giving us heat because we have a heating system in our school so we don't freeze. Does that make sense? All of these energies can be converted from one form to another. Do you guys know where radiant energy comes from? It's radiation, yeah. What is the main source of radiation on our Earth, actually? Anybody know? The sun, yeah. Yeah, the sun will actually give us the whole electromagnetic spectrum. And so much of that is in the form of, say, light, but there's other forms of radiation as well. X-rays, for example, would be another type of energy. Okay. Nuclear energy, like in, say, like a nuclear power plant. There's another form of energy. We use this to give us heat, usually. If you take physics, we'll talk about how magnets have a form of energy in them. Because really, why does this magnet and this magnet want to eventually stick together? Well, there's a form of energy between them. What's an elastic energy? Think of a slingshot. I pull back a slingshot, and I let it go, and all of a sudden the thing that I put in the slingshot is able to fling forward with energy. The elastic has energy in it. Okay. There's a lot of different things that you might not realize have elastic energy. For example, a basketball. It actually works based on elastic energy. What's supposed to happen when you bounce a basketball is the ball is going to eventually hit the ground. You know what actually happens if you were to slow-mo and like take like a time-lapse camera? Is it actually like compresses and like the basketball will warp. Has anybody ever seen pictures of like athletes, like say a tennis player, a hockey player, a basketball player, and they do like a super high def shot, and you can see like the hockey stick flex or the tennis ball like warping? Anybody ever seen some of those photos? That's elastic energy, where something is compressing and then it springs back outwards. Does that make sense? That's what a basketball does. A basketball will actually slightly compress in, and then it'll spring back outwards, which is why when it re-inflates itself, it bounces back out. Sound, I hope that makes sense on its own. Mechanical energy is actually an overall term we use to describe all of the energy in a system. So mechanical energy is often used to describe all of these. Okay. Luminous is light. This last one here is well beyond what we'll do in grade 9, but I want to be thorough. I want to explain to you where we're going at one point. There's actually something called mass energy, and I feel like most of you have actually seen this formula before. Albert Einstein realized that there's a formula known as E equals mc squared. Anyone ever heard of this one before? This is the mass energy formula. This is mass right here, and mass can be used to create energy. And if you take Physics 30 with me, I'll show you how this works in more detail. So, anyways, here's the point I wanted to make on this slide. I need you guys to be aware of all the different types of energy that exist. But energy is not matter. They're different. Energy is what's used to move and do stuff to matter. Does that make sense? So let me go back to where I kind of left off here, because I got away from my point here. Count Rumsford, if I can go back to his last idea here, he then realized that there was no such thing as caloric, but that really just energy was moving. And that this moving energy right here caused this moving energy, caused this moving energy, and then eventually, someone said this earlier today, but two surfaces that are next to each other are going to undergo friction. And friction then is what gave us heat. And so it didn't come from nowhere. It's not like heat just randomly showed up. It came from the energy in the horses. Does that make sense? Okay. I talked about the divide between classic and modern physics. We now know energy a lot better because of further understanding of our universe. And so I want to talk here about how, you guys know how we sometimes use the word energy to refer to like having stamina? Like I might say, I have no energy today. You know, that's not what we're talking about though. Like if you're saying that I need some energy because you drink a 5-hour energy drink, that's not really the same thing though. Does that make sense? Energy in the physics sense is really based on this. Energy is the ability to do some sort of work. If you can perform some sort of useful task, that means you have energy. Does a light bulb perform some sort of work or some sort of task? Yeah. Okay. Therefore, it lights up the room. That is doing work. That means light is a form of energy. Does that make sense? So it's really not the same thing. If you're talking about this person here having no energy, that's not quite the same thing that we're talking about. We use the words interchangeably, but really in a physics sense, energy has to be like something that gives you a task. Now, what sort of energy gives humans the ability to get up and move? Does anybody know on that list that was there previously, wherever it was right here? Does anybody know which of these energies right here gives humans the ability to get around and move? Say it. Yeah, chemical energy. Yeah. Where do we get our chemical energy from? Food. We eat food, and there's chemical energy in the bonds that holds the food together, and then that eventually gets converted to the energy that we use. But it's not really fair to say that we have energy. It's more that like our body cells have chemical energy. Has anybody ever heard of a mitochondria before? I'm pretty sure that's last year's curriculum. Yeah, cells have a mitochondria which stores your chemical energy. Does that make sense? So I don't want you to talk about a person having energy. Talk about a person having chemical energy in their mitochondria. Energy is kind of a hard thing to define, though. What I need you guys to be aware of, though, is that energy can be transformed. If you can follow that bit there, then it can go from heat to light to sound. That's the basic idea here. One last slide here, and then I'm going to get on to more of our focus on electrical energy here. Of all the different forms of energy, the Greek root of the word energy is energos. It means active. The whole point of this meaning that like for it to be energy, you have to do something. Okay? So let me go back to the very, very first thing I talked about. What is physics about? Physics is the study of natural things. What are we going to study? Stuff, matter, and energy, how it does something, how it's going to actively cause something to have motion. Okay? It has to move. It has to do something. If it doesn't do anything, there's no energy involved. Okay, I feel like I've been super redundant. Do you guys feel like you got my main points here? Okay, because we're actually not studying energy in general. We're going to study specifically electrical energy. So I'm going to skip these slides. You guys can just read them later. Here's a slide about chemical energy. Here's a slide about electrical energy, nuclear and solar energy. Let's start here now. My job in Science 9 is to specifically teach you about electrical energy. Okay? We will learn about all the other types at some point in your science careers, I guess. But we're going to talk specifically about electrical energy. And the cool thing about electrical energy is it's one that really binds with all the rest of them. For example, imagine a toaster. What does a toaster do? Well, it takes electricity and it turns it into heat so that it can toast your toast. Right? What does a flashlight do? Well, a flashlight takes chemical energy in a battery, it turns it into electricity, and that electricity eventually turns it into light. What does a blender do? A blender takes electricity and turns it into mechanical energy, like motion, basically. What does a battery-operated clock do? Well, it takes a battery, chemical energy, turns it into electricity, and eventually turns it into sound so that you can wake up. Here's the point I want to make. Which thing was on every single one of these devices? Electrical. In the modern world in which we live in, We use electricity for so many things. If I were to teach you this science class 100 years ago, I don't think we would have fully known about electricity. Does that make sense? But nowadays, everything we use runs on electricity. So I think that's why it's such a cool unit, because that's what we're going to focus on. So, first thing we're going to talk about, just like in chemistry, we should talk about safety. Okay? Because before we're actually going to utilize electricity, we should know what it is we're doing. Okay? Electricity can be very, very dangerous. It does a lot of cool things, right? It is powering your cell phones. It's powering our lights. It's allowing our furnace to run so we have heat. But in all of these cases, we need to be careful that we don't electrocute ourselves. You guys have heard that phrase before, electrocuting yourselves? Okay. So here's some stuff I want you guys to write down here. You know what electricity tries to do is it tries to find the shortest circuit possible. We're going to build circuits today. And hopefully you guys are somewhat aware that like for electricity to run, it needs to run through wires. That's not new information to you guys, right? Okay. Well, it doesn't have to run through wires though. Electricity can run through many different things. It's just wires are a very convenient way of doing that. When we talk about electricity in a few minutes here, lightning. Lightning is a form of electricity. But does lightning necessarily run through a wire? No, but it's super dangerous. Okay, so it wants to find the shortest circuit possible. If it happens to go through a human body, it's very dangerous. Okay, you don't want to get hit by lightning. Okay, that's dangerous. Okay, I don't think you do, because it very likely will kill you. So I need you guys to maybe highlight this. In our unit here, there's going to be a few more times where you just need to memorize facts. And this would be a good one of those times where you need to memorize this fact. Okay? If you have a really, really low amount of amps, like these numbers right here, we can actually use low amounts of electricity to shock people. Does anybody know what a joy buzzer is? What's a joy buzzer? Yeah, so it's like one of those pranks where you put a joy buzzer in your palm of your hand, you go shake somebody's hand, and they go, right? Because what you've done is you've given them a mild electric shock, okay? And we actually can use electricity to do things like even to try to relax or tighten muscles. So if you use a low amount of amps, it usually either shocks somebody or changes the way their muscles contract. But if you start to increase the amount of amperage, and take a look at these numbers here. This was 0.015. All it takes is getting up to about this, 0.01 amps. And it's enough to be fatal. Because here's what happens. If you have too much amperage, it will actually burn and damage your heart. And eventually it'll cause your heart to stop. Most places in the United States that have the death penalty, they now use chemicals to stop someone's heart. But it used to be that they used to have the electric chair. You guys ever heard of one of those before? Yeah, right? Now what is it doing there? The electric chair is literally, it's causing so much electricity to go through your body that eventually it causes your heart to stop. Does that make sense? We actually have something that does the opposite of that. It's called a defibrillator. It's supposed to start to restart your heart. Okay? So we know that electricity causes some problems to the human body. Long story short, we got to be careful. Okay? Because you don't want to mess around with electricity. So you guys have seen one of these things before, right? Like a high voltage box. They tell you don't play by high voltage boxes for a reason, right? Because you don't want to get electrocuted as a little kid. So now, one thing I want you guys to know that it's actually not the voltage that matters. This is actually a common misbelief, but it's actually not voltage that kills you. It's actually the amps. And later on in our course, I'm going to explain to you the difference between V, which is volts, and A, which is amps. Okay. We'll talk about that later because I don't want to bite off too much at a time. But this right here is actually a voltage box. Okay. Now, here's the thing. Usually when you have high volts, you also have high amps. But it is actually possible to have a lot of voltage but have low amps and have it be safe. You guys get what I'm saying here? So, but if you want to know what it actually is that hurts, it's amps. A for amps. That's what's dangerous. Okay. Now, people have discovered then that there are some things that are great at conducting electricity, but there's some things that don't conduct electricity, like at all. And we use those to help us stay safe. You guys have probably heard these words before. Conductors and insulators. Anybody ever heard those before? Okay, now a conductor, we're not talking the person who conducts the band kind of thing there, but like a conductor makes electricity go through it. An insulator doesn't. And I know I have this on a future slide, but like for example, there are some things that are good insulators like glass, or a really good one is rubber. Rubber is a good insulator. If you want to keep from getting electrocuted, put rubber gloves on. It's actually a reason why your car is actually a very safe place to be during a lightning storm. Does anybody know why? Rubber tires, yeah. And because of that, electricity will not pass through your car because it can't go through the rubber in your tires. Does that make sense? Otherwise, a car would be very dangerous because it's made of metal. And most metals are usually really good conductors. Okay. Now, if you take more and more science with me, eventually we're going to talk about something called an electronegativity. And it's actually a good way to know who's good at conducting electricity and who's not. I don't need you to know this for this course, but there's actually a way for us to know which elements on a periodic table conduct. And if you guys still have your old chemistry periodic tables nearby, you can actually find on that table where it tells you about electronegativity. Basically, the idea is the higher the electronegativity, the more stuff conducts. The lower the electronegativity, the less it conducts. But we're not going to focus on that. I think this picture, though, is really good for us to be able to see this. Okay? The reason why things conduct is due to positive and negative charges. This is why we got to do this unit after chemistry. What are the positive charges in atoms? Positives are due to protons, yeah. And the negatives are electrons, yeah. And so there are some things that when you look at them right here, the positives and negatives, they stay together. These things right here, they do not form ions. You guys remember that word from chemistry? Ions. Where something either gains or loses electrons. These guys right here are still neutral. But can you see how these guys right here, how the electrons are now starting to separate from the positives? If an item has the ability to have separation of positives and negatives, then electricity can flow through it. And if they all line up in the same direction and the electrons start going the same way, then that's electricity. I want to say that again. If everything starts lining up in the same direction and the electrons start to flow, that is literally the definition of electricity. Electricity is electrons that move. Let me say that again. Electricity is electrons that move. Say that one more time. This is so important. What is electricity? Electrons that move. Yeah. These guys right here, can the electrons move? No, they're stuck to the protons. So these would be things that don't conduct electricity. Now, can you see how these electrons in this picture here, they're kind of just like randomly going any which direction? This is still not electron flow because the electrons are not all moving in the same direction. See, this one's going this way, this one's going that way. They're just kind of going in random order. But if you can get all of the electrons to keep traveling in the same direction, that's electricity. Does that make sense? And certain things are great at conducting electricity. Other things aren't. So there's actually like a spectrum of things. It's actually not just insulators and conductors. If you get to a high enough level, yes, you need to know these two terms. But there's actually things called semiconductors and superconductors. And I thought I'd share these with you because they're actually really cool. Okay? A semiconductor, as you might imagine, sometimes conducts electricity. And sometimes it doesn't. It's kind of in the middle. These guys don't conduct. These guys do conduct. These guys sometimes conduct. And I'm going to show you why that's useful in a future slide. Superconductors, not only do they conduct, but they conduct really, really well. Hence the name superconductors. Like they're super at their job. Okay. So what I'd like to do is show you some of those on this next couple slides here. Here are some examples of some things that can conduct electricity. And many of them are metals. Like here I've got some tacks or aluminum foil. But this is actually a picture of an orange, if you didn't know this. Anybody ever seen a potato clock before? A potato clock. Literally what you can do is you can take two pieces of metal, put them inside a potato, and it can actually conduct electricity. Oranges will actually also do that as well. If you've ever seen one of these, maybe I'll make one later. Here are some examples of things down here that don't conduct electricity. Wood, glass, and rubber. And so we usually use these to protect ourselves and insulate us. But there's some things in the middle that are known as the semiconductors, where sometimes they conduct, sometimes they don't. And we use these in our electrical devices because sometimes we would really like to be able to take our devices and turn them off. Does that make sense? We don't always want them running. Does that make sense? And so semiconductors have the ability to have things like transistors or computer chips so that sometimes they run and then sometimes they don't run. And so if I ever ask you, give me an example of a semiconductor, you may want to write these ones down. Here's two good examples. Germanium and silicon are both well-known semiconductors. Now, because I've taught you guys chemistry, I want to find these on the periodic table. So I'm going to go back over here so you guys can see. I'm going to bring a meter stick. Here is silicon. Here is germanium. Can you guys see those two right there? Okay. Metals. They like to conduct. Non-metals. They don't like to conduct. But do you guys remember what we call the things on the staircase? Yeah, metalloids. Well, guess what? Silicon and germanium, they're both metalloids, which means that sometimes they conduct and sometimes they don't conduct. And if we can find a way to turn them on and off, well, that's how you make transistors and circuitry. And we use that all the time in these sorts of like computer chip stuff. Does that make sense? So this didn't exist 100 years ago, by the way, right? Like, we didn't know about this. One of the most common places that you'd actually find a semiconductor is in a photocopier, actually. So I put a picture of this here. Because what ends up happening in a photocopier is that it really depends on temperature as to whether or not it conducts. I'm going to read out loud off my slide. I rarely do this, but I'm going to read this section right here. Semiconductors are capable of conducting electricity, but it depends on the conditions, such as temperature. At low temperatures, they insulate, but at room temperature and above, they conduct. And so like what a photocopier might do is once you heat it up, anybody ever notice the photocopier has to get heated up and get warm first? Then, when it's ready to be used, then it will actually take the print and photocopy what your paper is, right? But when you turn it back off, it cools back down. Well, then it doesn't work anymore. Does that make sense? So there are actually certain things where they have to be warm. This is a reason why a lot of electrical devices don't work in the cold. Okay, and like a car, for example. You know how a car doesn't necessarily turn over in really cold conditions, like if it's minus 40 out. This is kind of the same basic principle, is that sometimes you need it to be warmer for it to conduct electricity, right? If it's too cold, it doesn't work as well. This is a slide I have about superconductors. Anybody watch The Big Bang Theory? There's been some episodes in the last couple of years where Sheldon, Leonard, and Howard are working on some sort of project for NASA. And they're working on other stuff, don't get me wrong. But one of the things they mentioned is how they needed to find something to be a superconductor. And I believe they used liquid helium in one of the episodes. Trying to think back. They were trying to like get it off the black market from one guy. And like they were feeling really bad about doing it. Anyways, if you use like liquid helium or liquid nitrogen and you freeze things to like the lowest possible temperatures, like -200, we've discovered things that are called superconductors, where basically there is no energy loss whatsoever. When the electrons go flying through the wires, there's no, the word we're going to use is resistance. Okay? It's a word we're going to use over the next couple of lessons, is resistance. All devices have at least some resistance. The more resistance you have, the slower the electrons go. Well, if you can lower the resistance to basically nothing, these devices work very efficiently. So anyways, one of the ways that we do that is use a superconductor at like absolute zero, like with liquid nitrogen. It's really cool. This is a picture right here of maglev technology, I believe. Anybody ever heard of maglev technology? Yeah, it's magnetic levitation. And basically the idea is you'd use a couple of magnets next to each other. They would appear to levitate based on how magnets work. And then there would be no resistance to air and friction. And so they wouldn't slow down. It's cool stuff. Okay, anyways, I should get back onto my topic because I'm slowing down and I want to finish by the end of class. So what I need you guys to know, because I go a little bit beyond what you're going to get tested on, but I need you guys to know about insulators. So here would be 3. If I were to ask you to name me some insulators, Wood, rubber, air, they're all good insulators. And I threw a picture on here of these rubber gloves because if you were working with high voltage and high amps, you would want to wear rubber so that you don't conduct electricity so you don't die. Okay. Now, there's also another safety thing I want you guys to know about. It's called the three-prong plug-in. You guys know how like there's some devices where there's only like 2 plugs to them? But then there's some that have that third one that goes down here. You guys know what I'm talking about here? Okay. I need you guys to know why that exists. If you haven't heard before, it's known as a ground wire. And I want to show you in some slides how this works. Here's a picture of basically how electricity works. It's supposed to go in a circuit through the wires in your wall. You have your main electrical pattern, and what happens is a hot wire brings electricity through the wire like this. Well, then you're going to plug in your device, and so it's going to cause electricity to go through here into, say, your device. I can't draw very well. And then the electricity will keep going back through the other plug and go back to where it starts from. And it's going to do a continuous loop. So it's going to go through the wall, through your device, back into the wall. So that's why you need 2 plug-ins. One is the hot wire. It's the one that the electricity is coming through, but the second wire is the one that the electricity is going back to the wall through. Does that make sense? It has to be on a loop, a circuit. Good. So you actually have what's known as the neutral wire and the hot wire, but newer devices, especially ones that you're worried about electrocuting yourself with, they have that third little plug, that little round one in the middle, right? It's known as the ground wire. And I want to show you on my next slides why a ground wire is important. So here's some pictures I have. This picture here is about a person who does not have a ground wire. And I want to explain what would happen here. Here's like the transformer on like the electrical panel outside your house. Okay? So this is where the electricity is basically being stored. And you're going to have a hot wire that's going like this. So the electricity is coming into your house, and then it's going into some sort of device. I don't care what the device is here, so it's just a box. Right? Then the electricity is supposed to go back through the neutral wire all the way back to the terminal. That's the way it's supposed to go. But if you get electrocuted, here's what's happening instead. I'll use another color. The electricity, let's see, red. The electricity is coming in through the house like this, and it's coming down into the device. But let's say that you get electrocuted. It would then go through your body and maybe through the ground and back up again. Do you see how that makes a loop? Now, I put down on one of my very, very, very first slides here, where was it? Electricity attempts to find the shortest circuit possible. If electricity can find a circuit that goes through your body, it will. And we don't want that. Does that make sense? So we would like the electricity to take the purple route right here. But if something goes wrong and it goes through here, through your body, through the ground and back up, and it makes a loop like this, you get electrocuted. We don't want that. So here's a follow-up picture that looks almost the exact same. Here's a follow-up picture. We're heading it off of the pass. We're going to say, rather than having it accidentally go through you and then through the ground, a ground wire literally goes into the ground. That's why they call it a ground wire. So let me show you that same picture again. Here, the hot wire is coming from the transformer through here, but that third little prong right there, it's attached to a wire inside your house that literally it goes to the ground and around again. So in case someone's going to get electrocuted, it doesn't go through you, it goes through the wire instead. Does that make sense? That's literally why it's called a ground wire. So that rather than the electricity trying to get to the ground, rather than jumping through your body, it will literally go through this third little prong right here instead, and hopefully save you instead. Does that make sense? Never cut those off. If you have like one of those three things there, and like you only have like a 2-piece one to put it into, get the proper extension cord. Don't mess around with that. Okay. Here's a picture I have talking about lightning, because lightning really does the exact same thing. And lightning can hit with as much as 30,000 amps. What does it take to kill you? 0.1. 0.1 could kill you. Lightning is 30,000. Now, don't get me wrong. People have lived from a lightning strike, but that's not likely. Okay, 30,000 amps is more than enough to be lethal. And so there's a lot of buildings that will actually have what's called a lightning rod. Anybody ever heard of these before? Literally what it is it's a piece of metal that's designed to have the electricity from the lightning hit it and then go directly to the ground. And so, like, I found a picture of a barn here. I found another picture on here. Rather than having, like, the building get struck and then maybe a person inside the building gets electrocuted, that'd be bad, right? They design a little piece of metal up on the top, these little antennas, so that lightning comes in and it strikes, there's a lightning bolt, strikes the lightning rod, and then the electricity goes directly to the ground and doesn't accidentally go through the building and kill everybody inside. That makes sense? So it's actually quite clever. Very important for safety. Most of them should have something like that, or maybe it wouldn't need one though because it's made out of insulators. Like, for example, our school, if it was made out of brick or wood, it wouldn't be as big of an issue. But if our building was made out of pure metal, like, say, a barn might have sheet metal on the outside, then you'd be more worried about it because the metal can conduct electricity. Does that make sense? I'm not really worried about brick or styrofoam maybe conducting electricity as well. But, like, big skyscrapers will. Okay, next slide about safety. Water and electricity are often very bad mixes. Okay, now, pure water actually does not conduct electricity, but most of the time water isn't pure. Normally there's stuff dissolved inside of it. You guys have probably heard this before. Don't, like, bring, like, your hair dryer into the bathtub because it could cause electricity to come from the hot wire through the hair dryer, and then rather than going back through the wire it's supposed to go through, it could go then through the water, through the person in the bathtub, down to the ground, and it could electrocute you. So don't mix water and electricity. You guys knew this though, right? That's not new information. Yeah. Okay, let's move on. I think I'm almost finished, right? Am I getting to the end here? Perfect. 2 more slides, then we'll call it a day. Thanks for staying with me, guys. Last thing I need you guys to know about. There are some safety devices that houses and electronics have to prevent in case of emergency. And the 2 things you need to know are a circuit breaker and a fuse. Anybody ever seen one of these in, like, the downstairs of their house probably? It's called a circuit breaker. Yeah. Basically what happens is if there was, like, an electrical surge, there's too much electricity, too much current running through a device. There's a spring inside this panel right here, and it'll cause these, like, little things to trip. And it'll turn off. It protects against electrical surges. Okay, it's called a circuit breaker, and if it happens, then you just got to go flip it back on and figure out what it is. My wife and I, we bought a new house, and we bought a new microwave, and the microwave uses like 1,500 watts, which is a lot of power, and it kept flipping the breaker on one of our panels, so we had to plug it into a different outlet because it was using too much power, and the breaker was recognizing that there was too much electricity surging through the wires, and so it flipped the switch and kept turning it off. It's quite annoying. These right here are known as fuses. Fuses are small things found within a device where it's a very, very small little piece of metal right here. Can you guys see this guy right here, how there's a big piece of metal on both sides, but there's just a little strip in the middle here. Electricity can go through that strip. But if there's too much electricity, too much current, too much voltage, what will end up happening is it'll get hot. And normally when things get hot, the problem is eventually it'll start a fire. Does that make sense? Both of these 2 things, the circuit breaker and the fuse, help prevent against fires because what happens is if it gets too hot, this little strip of metal here will break. And as soon as the strip of metal breaks, it breaks the circuit, and all of a sudden it'll turn off. And it means that you have like a blown fuse. Anybody ever heard that phrase before, like you blow a fuse? Right? Well, the idea basically is that this is the little weak link. And if this heats up too much, it'll break, and then it'll turn off. And that's its backup plan so that you don't end up having a fire. Okay? So fuses will then melt if there's too much current through it. And these circuit breakers, the word we sometimes use is they trip them. And so it's all about this. If it's going to get too hot, it could cause a fire. So this is our way of protecting against that. Okay, last slide, then we're going to take off here. This is just a summary here. I don't think I need to read through all of these because most of this is like common sense that you've learned before. But like, here's some basic electricity safety pointers. Like, stay away from power lines. Don't use broken or frayed cords. Stay out of water. Never remove the third prong from the device. So, quick summary. Why do we have to be careful with electricity? Why, though? How does it kill you? What does it do? Finds the shortest circuit, and if it goes through your body, it messes with your heart specifically. It could stop your heart. Yeah. Okay? Yeah, it actually doesn't take a lot for it to actually stop your heart. Okay. Do you guys have any questions for me? Okay. Come here tomorrow, but I'm pretty sure that most of our class tomorrow is during the Remembrance Day Assembly. So I don't actually have any plans for tomorrow otherwise. So it's at 9:30, right? Yeah, which on a Friday class is going to be like right in the middle of our class. Okay. So I will try to get the rest of our notes and assignments on my website so you guys can print them off like tonight or tomorrow. Yeah. Okay. Okay, you guys can take off. It's basically flex time here.